Hello everyone, welcome back. In this video, we'll be looking at associativity and commutativity of natural numbers. So, what we take for granted, such as associativity and commutativity, isn't really so pretty trivial. We first need to prove them before we're using that. All we know is that n plus 1 is equal to the success of n. We don't know that 1 plus n is also equal to the success of n. So let's begin first by proving associativity of natural numbers. To do this proof, we'll use the fourth piano axiom. So we define a subset K such that let K equal such that all its elements are in the natural numbers, and it follows the property L plus M plus N is equal to L plus M plus N. So if we're able to prove that this subset of the natural numbers follows this property, then automatically we'll be proving that the natural numbers themselves also prove this property, because this is just a subset of the natural numbers. So if you remember from the previous video, from the fourth axiom, the fourth piano axiom, any subset of the natural numbers should follow two properties. The first one is 1 should be in K, and the second one is the successor of n should also be in K if n is in K. So let's begin by proving the first property. So we'll replace n with m. So for 1 is in K, L plus m plus 1 is equal to L plus m plus 1. Right, let's see how we can do this. So we need to show that the left hand side is equal to the right hand side. So let's begin with the left hand side. If we are able to show that the left hand side is equal to the right hand side, our proof is done. So L plus m in brackets plus 1 is the same as successor of L plus m. Remember this from the first property of addition. We're just replacing n with L plus m. This n right here, we're replacing it with L plus m. Now from the second property of addition, we get this L plus successor of m. Right, from the second property of addition we get this. Now remember that successor of m is m plus 1, right, from the first property of addition. So we can write this as L plus m plus 1, and we're done. The left hand side looks exactly like the right hand side, so we're done with proving the first property. Now let's prove the second property, which is we have to prove that successor of n is also in K. Whenever n is in K, the successor of n is also in K. So we're going to start this way. L plus m plus, we're replacing n with the successor of n, is equal to L plus m plus successor of n. So just like the previous part, we have to make the left hand side look like the right hand side. You can choose any side you want to do and show it to be equal to the other side. So I'm going to start with the right hand side and try show that it's equal to the left hand side. So this is the same as the right hand side. It's the same as writing L plus successor of m plus n. Remember this from the second rule of addition, which in turn is the same as successor of L plus m plus n. Also, this is from the second property of addition. We're taking the whole m plus n term as one term. So we're replacing n plus n as m and L as n from here. So that's how we get here. Now we can also write this as successor of L plus M brackets plus N. Well, we haven't proved associativity yet. How can we write this? Well, because we have created a subset right over here, which assumes this property, where all the natural numbers, all the elements in K have this property. So this right here looks just like this right over here when we define the subset. So we can replace this with this term right here, which that's what we did right now. Now this is just equal to L plus M plus successor of N. We get this from the second property of addition. I hope you see how we're getting this, because L plus, we're replacing this N term right here is the L plus M term right here, and the N over here is the M over here. So we're replacing this with this. So, and we're done with the proof. The left hand side looks exactly like the right hand side. So we're done with the proof, and we've just proved the associativity of natural numbers. So QED. Now let's go on and prove commutativity of natural numbers. Right, we know addition is commutative, but I want you guys to forget the number system we have now. We're building a new number system right from the scratch. So let's see how we can prove that addition is commutative. Right, I think we'll follow the same pattern we did before. We define a new subset of the natural numbers such that k equals n in the natural numbers, such that they follow n plus m is equal to m plus n. Right, let's go with the proof of this. We'll follow the same template. We'll try do both the properties of the subset. So first we have to prove that 1 is in K. So 1, we have to show that 1 plus m is equal to m plus 1. Well, we know this is true, but we haven't proved commutativity yet, so we can't say these two are the same. All we know is n plus 1 is success of n. We don't know 1 plus n is the same as n plus 1. So we don't know yet that 1 plus m is equal to m plus 1. Remember, we're building our number system from the scratch, so we can't assume anything. So to do this, we'll define a new subset. Let K tilde, this is a new subset, this is not K, this is K tilde, such that all m are in the natural numbers. Remember, over here we did all n are in the natural numbers, now we're doing all m. So this m right here. So all m are in the natural numbers such that m plus 1 is equal to 1 plus m. So we have just defined a new subset of the natural numbers so that they follow this rule. So now let's prove the two properties for this new subset we did. So let's do 1 tilde. So remember, for 1 tilde we have to prove that 1 is in K tilde, which is just we're replacing now m because we defined it as m with 1. So 1 plus 1 is equal to 1 plus 1. Now LHS, the left hand side looks exactly like the right hand side, so we're done with this part. Now for 2 tilde, let's prove that the successor of m is also in K tilde. So we're going to replace m with the successor of m, so we're going to write it this way: successor of m plus 1 is equal to 1 plus successor of m. Right, now you can choose whatever side you want to, and try make it is as equal to the right hand side or the left hand side. So I'm going to start with the right hand side and try make it look like the left hand side. So this we can write it as successor of 1 plus m, which we can in turn write it as successor of m plus 1. Remember this because m is in K tilde, and we just defined k tilde to follow this property. So m plus 1 is equal to 1 plus m in k tilde, and we're proving that success of m is in k tilde. So we know that 1 plus m is equal to m plus 1 in k tilde. We don't know it's the same in natural numbers yet. So this we can write it as success of m plus 1. This is from the second rule of addition. Now the left hand side looks exactly like the right hand side. So we're done with the proof of 2 tilde. So remember this, we're still proving 1. So since we've proved this, we've proved k tilde to be this, we have proved that 1 is the 1 is in k is true. So now we have to do the second property of the subset of natural numbers, which is we have to prove success of n is in k. So I hope you're getting this. I hope you understand that all this work we did was just to prove this, that 1 is in k, was to prove that this is true. So we did that right here. So we did that right here. So we have proved that 1 is true. Now we have to prove the success of n is in k. Okay, to do that, we have to replace n with the success of k. So we're going to write it this way. N success of n plus m equals to m plus successor of n. Right, we have to make just like we did before, we have to make the left hand side look like the right hand side. So how are we going to do this? Well, let's start by evaluating the right hand side. You can also start with the left hand side, but I'm going to start with the right hand side and try make it look like the left hand side. Right, the right hand side is m plus success of n, which is the same as m plus n plus 1. Remember this, we get it from the second rule, the first rule of addition. Success of n is the same as is equal to n plus 1. So now we can write it as m plus n brackets plus 1. Remember we get this from the associativity of addition, which we proved it before. So we can now rearrange the brackets the way we want it because we proved it before. So we can use the theorem we proved before to prove the commutativity of addition. Okay, now let's write it this way. 1 plus m plus n. Okay, how did we do this? Well, this is because we defined k to be this way. N plus m is equal to m plus n. So this is n and this is m. So we can just switch the positions because this is in k. In k, we define the subset to be like this. So we can just rearrange the order. And I'm going to do that again right here. 1 plus n plus m. This is also because we defined k such that n plus m is equal to m plus n. So m plus n right here is equal to n plus m right here. So I hope you're getting this. If we can prove that this subset of the natural numbers follows this rule, then automatically all of the natural numbers will follow the rule, because we can just choose the natural numbers to be the subset of this to be the subset. We can choose k to be the set of natural numbers itself. So what next? We can further write this as, we wrote it as 1 plus n plus m. We can further write this as 1 plus n plus m. Well, this is also from the associativity of the natural numbers, which we proved before. We can further write this as n plus 1 plus m. I'm sorry about this. N plus 1 plus m. Well, how did we write 1 plus n as the same as n plus 1? Because we proved it right here that 1 plus m is the same as 1 plus m plus 1. if you can see it over here, we proved that since 1 is in k, 1 plus m is equal to m plus 1. Therefore, we can write it as 1 plus n is the same as n plus 1. And now n plus 1 is the same as the successor of n plus m. Remember, we get this from the first rule of addition. So now the left hand side looks exactly like the right hand side. So we're done with the proof, QED, and we've just proved the commutativity of addition of natural numbers. Remember that we proved this for the subset of the natural numbers. So if the subset of the natural numbers follows the commutativity and associativity, the whole natural numbers itself will also follow commutativity and associativity. Now let's look at an example of how useful the theorem we proved is. So we were told to prove this part right here. Well, we know it's exactly the same, but we know it's exactly the same because for years and years we've been doing addition. But this simple stuff right here, we can now be able to say confidently is the same because we've proved the theorems for associativity and the commutativity. So let's see how these two are equal. So I'm starting with the right hand side. You guys for practice can do the left hand side and show that it's the same as the right hand side. So we start with the right hand side right here, and this is the same as this because of associativity. I'm just rearranging the brackets to here. Then d plus a plus c, d plus the brackets a plus c is the same as in brackets d plus a plus c because I'm just rearranging the brackets the way I want it to be. And then I'm using commutativity to show that d plus a is the same as a plus d. Then I'm using associativity again to show to rearrange the brackets uh, this way. So I'm using associativity again. Then I'm using commutativity again to show that d plus c is the same as c plus d. Then associativity again to rearrange the brackets the way I want it to be. And then I'm using commutativity again to show that c plus d plus b is the same as b plus c plus d. Then I'm using associativity again to show that b plus in brackets c plus d is the same as in brackets b plus c plus d. I'm just rearranging the brackets over here. Then I'm using associativity again to rearrange the brackets again to put it right there. Then the final step, I'm just using associativity just again to move the brackets from b plus c to a plus b, and we're done. The left hand side looks exactly like the right hand side. So we've just proved the associativity and commutativity of natural numbers for addition. So I hope you guys get this. Just try to start from the left hand side and show it's equal to the right hand side for practice. Hope you had a great time. See you next video.